Hi, Matt Norman here from Oak Ridge, Tennessee at Oak Ridge National Lab. I work in the Scientific Computing Group, and I'm going to talk about some methods that, given the last three talks, you might be disappointed that I'm neither Lagrangian nor implicit, but coming from the other side of things. But just talk about some methods that are going to scale in modern computing. I wanted to start off this slide with the title that computers are changing, but the fact is that they really have changed. And they're still in the process of changing. And I don't just say that because Oak Ridge has a Lagrange basis. So, and that actually has p to the negative 1.3. So that's nicer than Galerkin. You're getting time step up a little bit. Multi-moment finite volume method. And I'll describe that in the next slide. What's really interesting about that is it's actually p to the 0. You can add as many moments as you want. 50th order accuracy has no smaller a time step than first order accuracy, which is pretty cool. I mean, it's obviously not going to be a free lunch. You actually have to limit those derivatives, and if the fluid is not smooth, then the derivatives actually contaminate your solution. So that's something to keep in mind. But you can add legitimate information as long as you have the smoothness available and you don't pay any time step penalty for it. And all of these methods converge exponentially, but not at the same rate. You have a different coefficient up there in the exponential. What is multi-moment finite volume? You're storing cell average derivatives of the flux vector, of the state vector u. And you evolve these just with derivatives of the PDE, and then you integrate that in space. And so it looks exactly the same as your original, finite volume method. You have a cell average variable, and then a flux, and a source term. You just differentiate those, and that gives you what you need to advance the solution. But remember, these are polynomials because I use the ADER scheme, and so you can do the differentiation and all of your things automatically with just dot products and matrix vector products. It's pretty quick to put through, and a lot of the matrices are triangular because you're using the derivatives. For the fluxes, I use a flux vector version of the F-Waves Riemann solver in Levesque's Big Red Book. What I like about this is you can time average your fluxes at the interface, and you only need one Riemann solver per time step at the interface. You can directly put the time average fluxes in. Since F-Waves use the flux directly to create the characteristic variables, you just crank it out. It's only one Riemann solve for the derivatives. So the real question is, what are you getting for the amount of time you put in? So I decided to go crazy and actually plot the L1 error for a shallow water system that's smooth versus the CPU cycles you took to get that error. And so this comes with all the caveats. Yeah, I tried to optimize each method. Just take my word on that. I really don't favor any of them. I just like multi-moment. This is on my Mac using an Intel 12 compiler with the dash fast and double precision. I use the Pappy hooks to get the cycles out. What we're seeing here is basically the SSP RK4 nodal discontinuous Galerkin method. This is very similar to spectral element. It's just a flux instead of an averaging, and it's about 10% more expensive than spectral element. It has about the same efficiency in serial as the ADER multi-moment finite volume method, which I consider to be a pretty good result because in parallel you're going to have a larger time step and less parallel communication. So it's going to win out in the long run. Your spectral volume method is less efficient out here in blue. And the ADER DG method really didn't pay off. The ADER time step ended to be p to the negative 2 instead of p to the negative 1.7, so the time step was killing me as far as the efficiency there. I also implemented a Hermite-Wiener, which stands for weighted essentially non-oscillatory method. If you're curious, I can talk about that later with you. I implemented that method. What's really cool is that it's actually here in the mix. It's not way out there as far as expense. You get a lot of accuracy, and you don't pay that much computation for it. And remember, this method is robust even to Mach 10 shock reflections and crazy things like that. It's already limited. Your discontinuities have been sufficiently diffused, but only where you need it. So that's kind of giving you an idea. I mean, this is for a really smooth flow. Nothing's ever smooth in the atmosphere, so the real question is how does it perform when limited? And time will have to tell. parallel communication, what I did was I looked at how many stages of parallel communication. Yes, I did go crazy out to 16th order, but maybe it's not so crazy if you don't have to pay the time step penalty and if you can limit those 16th order derivatives. Those are all ifs. But you have an ADER discontinuous Galerkin nodal method requires this many, sorry, these colors are the same. This is 16th and this is 4. This is how many stages of communication you have to do to get to a certain length of time, and I normalized it by the large time step here. And so, if we look at 8th order, maybe that's a little more reasonable. You're talking about, between 30 and 40 times less stages of communication with the multi-moment finite volume. In fairness, as a caveat, the multi-moment finite volume communicates the same as a modal DG, which means you have to communicate all the modes across the interface at a given time. And so it does communicate more per stage than nodal DG. But if latency is a big player in your MPI communication, meaning you don't have too much data going across, this is still a big payoff. So it depends on the problem and how much you're communicating, over the edge. So just throwing that in there. Thanks. So the Weno and Hermite-Weno methods with a multi-moment finite volume are robustly limiting oscillations. Here's a shock with a shallow water system. I can zoom in on this little area, and you can see how the blue triangles, the Hermite-Weno, is a little sharper in the discontinuity than the single moment Weno. Sorry to use all the jargon if you're not familiar with Weno schemes, but it's just showing that it can robustly limit shocks at this point. Flux-corrected transport is another option for limiting, and I'm sure there's some sort of reconstruction. Paul has some interesting ideas about how to use a modal limiting for some of the limit the recovery operator itself without having to use a stencil like Hermite-Weno or something. Conclusions, really I'm just trying to put out there's a lot of unexplored moments and a lot of unexplored ways to evolve them. And I think some of these are going to be a lot better for current and future parallel computers. And it's worth looking at. I don't think we've really populated the space, and we should at least investigate. ADER is a neat time discretization. It's fully coupled, nonlinear, over very large time steps. And considering the length of these time steps, it's actually very accurate compared to something like Runge-Kutta. And now, with some recent research with a colleague of mine, it's a lot cheaper. Spectral volume is an interesting alternative as well because it can use larger time steps than Galerkin depending on how you cluster the mesh. Multi-moment finite volume could be very useful. If we can limit these really high order derivatives, you can avoid a lot of communication, which could really pay off when you're going across an entire 500,000 core machine to pick up data from another node. Something that really needs to be looked at is for these really, really high order approximations, how can we limit these robustly while preserving as much variation as possible? You cannot flatten 16 derivatives and expect to get any efficiency out of your scheme. You need to save as much as possible and remain robust. And I don't really care much about monotonicity that much personally because you can just apply flux-corrected transport or something after the fact. But you just need to keep it non-oscillatory and as much variation as possible. And it's not, I haven't implemented it personally in multiple spatial dimensions, but it'd be really interesting to see how this expands out into 2 dimensions. Who ends up with more computation, Galerkin method or finite volume or spectral volume. So this is things to look at in the future. But with that, I'll finish and take any questions.
So, metric for these sorts of questions about communication versus computation that's recently become into fashion is arithmetic intensity.
Yes.
So, what's the tip? Can you give me some sense of what the arithmetic intensity is for some of these methods?
It's very high in everything except for one portion, and that is these differential transforms. You can see this is an extremely dependent loop. It's got a lot of triangular dependency. That is my only worry for these schemes. When you get to polynomial evaluations and averaging, those are dot products. That'll be just fine on a GPU. That can be separated into defined scale work. This is my biggest concern: is how do we handle this triangular loop that has to step down dependently from one point to another. And I have some ideas. So there's been, I think it was a molecular dynamics code that had to develop something called Suite 3D, where they just glued a bunch together. And once you kind of populate the array, you just keep going, down. And I'm hoping there's some way to do it there. But this is my biggest concern as far as that goes.
This ADER scheme, is it related to Lax-Wendorf?
Yeah, of course. Yeah, it's nothing fundamentally new. It's the modern Taylor method, which has been around for decades. It's just a new spin on it. And the differential transforms is a new application of something old to get it done quicker. So it is related to Lax-Wendorf, using spatial information to get temporal information. Yeah, it's exactly that.
So basically,
Yeah, so it's just the Cauchy-Kovalevsky theorem that you.
Yeah, Cauchy, yeah, that's exactly what it is.
But my question is not about that. It's about time integration.
Okay.
Do you see any issues with using these multi-moment finite volume methods in an implicit time integration scheme or implicit explicit, something like that?
I do not know what the matrix properties would be for an implicit scheme for multi-moment finite volume. That would be great to look at. I don't have a clue because I haven't even looked at it. Yeah.
Be interesting.
I don't know what the sparsity would look like or what the structure would be like. I just don't know. Yeah.
Okay, well, that's like not on the way of the stage.